Guys, thank you so much for having me. This is an amazing conference. I've had so much fun so far. Thank you to the organizers and this beautiful venue and our musicians. This is really exciting to be here. So what I want to do today, my talk is called Process Potential, and what I want to talk about is maybe reframing the way that we are making decisions around using processes and OTP in our apps. And the main question that I want to ask ourselves is this one. What is the potential of processes for a given application, and how do we make that determination as programmers? So when I'm talking about potential, we're talking about processes on two different levels, right? We can use processes just by virtue of coding in Elixir and Erlang. Our code is run on a process in the beam. That already gives us a lot of advantages. We can also take that to the next level, OTP. And what we've heard today has been super interesting, right? And I'm sure you've read the articles and listened to podcasts about you might need OTP, right? And I think sometimes when we're getting into those situations, we can see that grabbing for it when it's not necessary can sometimes lead to overcomplicated code or bottlenecks where we didn't need them. But when you have the right use case for it, taking advantage of OTP can really transform an application. The example that I want to use today is a program that I wrote with my coworkers last year. And what was cool is that we already had this functionality in our legacy Ruby on Rails app. So when we rebuilt that functionality in Elixir, it was a really cool comparison of the fault tolerance that we gained and the concurrency that we gained with Elixir. And what I want to do today is help us all get closer to making better decisions about when to use OTP by going through this app while we look through the foundations of OTP itself. I think that revisiting those building blocks can often give us a new perspective on how we can solve our current problems. So that's where I want to start. This is the app that we're going to be building up to. It's a course deployer, right? So at the Flatiron School, what we do is serve lessons to students. Those lessons are stored in repositories on GitHub. And basically what happens is we've got this one template repository, right? It's like a canonical material. We're going to clone that and fork it for our students. So I was a teacher, right? I would go in the morning and I would deploy, say, 10 lessons for 10 students, even though it was more like 20 lessons for 30 students. But let's just keep it simple, right? 10 lessons, 10 students. If I'm making that deploy, that means I'm essentially putting 100 repos on GitHub. So that in Ruby looked like using workers to keep that asynchronous so that we wouldn't be blocking other processes. When we went to rebuild this in Elixir, we decided to build it on top of OTP. OTP is, of course, an abstraction of and the ecosystem around processes. And processes come from this initial idea of message passing. So that's where I want to start, is message passing. So this is a basic premise. It's an idea that Carl Hewitt and Alan Kay were interested in the 1970s. So what this is these two entities can only communicate with each other through giving a message. So this human on the left, she's giving a message to the other human to please take out the garbage, but she can't force him to do anything, right? She can just give him a message and hope that he does with it the right thing. So this developed into what they called the actor model, this idea of message passing. So the actor model actually really influenced OO, and just like we've heard, everything in OO is an object, everything in the actor model is an actor. So each of these actors, they can send and receive messages, they have prescribed ways of responding to them, and early OO really took from this and resembled this. So let's move forward to Joe Armstrong. And Dave, thank you so much for giving us the context around him that you did. I feel like we should all be so lucky to have met him. And he came to Ericsson in 1985. When he came there, like Dave was talking about, his problem wasn't concurrency. That was already something that was happening. What he was trying to do was create reliability. So he starts looking around for solutions. And one of the things that he looks at is Smalltalk, which is an early object-oriented language developed by Alan Kay. Again, this was influenced by the actor model, so it had this idea of message passing between objects, right? But he had some problems with OO. He liked the idea of message passing, but there were some things that he didn't feel so great about. He has this quote that I like. He says, "The problem with object-oriented languages is they've got all this implicit environment around them. Maybe you wanted a banana, but what you got was a gorilla holding the banana, and the whole jungle around that." So this is a problem for him. He didn't like the binding of data to functions either, the way that we have objects with methods attached to them. He didn't like that mutable state was contained inside each object. So he moves forward and he wants to keep this idea of message passing between the actors, but throw away the overhead of that implicit environment. So we enter processes. Processes are isolated. They can't share memory with each other and they're by themselves, so they can run concurrently. They can send and receive messages. They're part of this big plan, but they don't really know anything about what's going on at the top. Let's just take a really super simple example of a process. This is a count up process, okay? So when we spawn a process, we're gonna get these special send and receive blocks. And if we were to spawn this process and start this execute method, let's say we give it the number 0 to start it with, right? So it starts up and it's gonna wait. It's gonna wait to get a message. Say that it gets the message add, it'll puts out to our terminal adding, and then it will call its method again, but add 1 to the number that came in first. So now we've got this number 1 coming in. And what this really gives us is this idea of storing state in a process that isn't going to be able to be changed by something outside of it, because we're simply sending messages to it. When we send the message finish counting, notice that we can put out to the screen, wow, we counted up to 3, but we don't call that execute method again. So it will die, the process is gonna die, it's not gonna wait for any more messages. So also notice that if it is waiting, if we call add and it gets to the top execute, if it's waiting, it's not working, like some of the talks said earlier. So this is how a process looks in the most simple way. And I've been trying to visualize this mapped to like a real world scenario, and a lot of like smart people have done this with cool analogies. One of the ones I like is the learn you some Erlang analogy, where there's like just a guy in a tower. There's like no windows, he's very isolated. But one of the things that kind of helps me think about this is processes being like spies. And can I ask real quick, can you raise your hand if you're a spy? Okay, Sophie, I'm sorry. I'm gonna take some creative license with spies from here on out, so don't judge me. But specifically, I think processes remind me of sleeper agents. So sleeper agents, they like are in this area of interest, and they only wake up when a task is given to them. They're not like going to spy meetings and sharing intelligence with each other or anything like that. They're not talking to other people. They're just by themselves in this area where they're going to perform tasks when they're told. So what would that maybe look like? Maybe this guy. So this guy is a spy, and he's in his secret bunker. And he's got an inbox for messages. He's got a writing table so he can send messages. He's got a legend on the wall so that he can map the messages coming into specific tasks. And he's got some formulas that he can execute whenever he gets that task in. So let's say he gets a message, right? If it doesn't match what's on the wall, he's gonna throw it away because it might be from the enemy. But if it does match what's on the wall, he's going to perform that task. He's going to make formula C. Notice that when he's making formula C, he might get another message in here, and he can't really do anything about it until he finishes his first task. So this is sort of like what we saw in the count up, right? It's gonna receive messages, perform tasks, wait for the next one. What's amazing is that while this spy is working on his tasks, we can have another spy over here working on her tasks. And we can keep scaling these spies because they're all running without shared memory in an isolated way, right? So this is a pretty cool thing that we can do with processes so far. The next concept that goes into the building blocks of what we're gonna do with OTP is linking. Let's say we've got spy A and spy B. Now they're both working on a super secret formula. We've given half of the formula to A and half of the formula to B, and they're gonna make something really special, but we can't let them know what it is. So in order to make sure that we maintain the integrity of our formula from these spies, we're going to link them together. And that way, if one dies, so will the other one. Now we've ensured that our formula can't be coming halfway to us. We just want to make sure that these two processes are linked, because that way we can like build up to greater things. So what if we want to know when a spy dies, but not kill the other spy? So let's pretend that that first spy is more like a spy captain in Spies Headquarters, and the second spy is just a worker spy. In this way, if this spy dies in the course of his work, this spy will just know about it, not die. Okay? And this is fun because Joe Armstrong broke this down like really simply when I was first learning about this. It made a lot of sense. It's like if one computer is working and doing its tasks, you need another computer to watch it and make sure that you can restart it or follow steps for remediation if it breaks, right? Okay, so what happens when eventually you get to failure? What happens when that process dies? So this was the piece that Joe Armstrong was most interested in, right? And the first thing is he said we have to expect it. And that was actually kind of revolutionary at the time. It wasn't in common thought. He talks about going to these distributed systems conferences and asking the presenters after each thing, like, what if one of the nodes fails? And their answer was basically, it won't. Which wasn't the answer he was looking for, right? So it seems that they were focused on this idea of defensive programming, guarding against things that would happen. And when we're talking about failure, the things that I'm kind of focusing on are the types of things that will happen in production that we can't replicate as easily in development. So this is a term for this kind of bug that would happen in production but is hard to replicate, is a transient bug. It's coined by Jim Gray, who studied these. And he found that almost 100% of the bugs he found in production were of this kind, the transient bugs. So how do you plan for these things that you don't know will happen? Because there are so many ways a process can fail. What if our spies' formulas expire and release toxic gas and it dies? What if enemies invade the bunker? What if a bug from another dimension comes in and wreaks havoc in the lab? I mean, we just don't know how to plan for these things. So what do? Well, we don't plan for them, actually. We don't guard against them in that same way. What Jim Gray found when he was studying these is the most effective way to get rid of them is to actually just wipe the whole environment clean and start over. Because when you can start a process over with the bug in it, you lose the bug and the process, but your process is cheap to restart. Now we're not spending developer time guarding against these things that are actually really hard to reproduce. So all of the things we've just talked about, the processes and linking and monitoring and failure tolerance, this is a spy system that is the basic pieces of Erlang. And we know that we're going to be relying on these things over and over again. And it's going to be kind of hard to manage these manually. So message sending, prioritizing processes, making sure we link them properly. Like, this is stuff that we kind of expect to happen. So that's where OTP comes in. OTP, of course, is orchestration of stealthy spies, which makes just as much sense as Open Telecom Protocol. So, but I do want to stop on that word orchestration, because that is really what we're talking about when we talk about OTP. It's like the Spy Headquarters. It's a training ground for these spies to go to so that they know the things that they have to do on your mission. Wouldn't it suck to get a spy who didn't know how to dress up in disguises? Because that is really important for spies. You wouldn't want that, right? So OTP is orchestrating these pieces of processes. It's abstracting the difficult parts of concurrency and fault tolerance for us so that we don't have to focus on that. We can focus on our application logic. We can focus on our missions. Francesco Cesarini, he founded Erlang Solutions. I was listening to a podcast when he referred to OTP as middleware. And I think that that's kind of a helpful way to think about it too. It's like not something that we're going to be coding directly, but we can use that to abstract the tricky things around processes. So let's move on to two of those OTP behaviors, GenServers and dynamic supervisors. And when we talk about OTP behaviors, GenServers and dynamic supervisors, we can think of it in a way that it's like a process taking on the behavior of one of these things. When we're talking about OTP behaviors, broadly, we're talking about the interface of them, like how we call on it, the implementation, how we're letting it know to respond to us, and the fact that it's running in the ecosystem. So how are we sending it messages? How are we telling it to respond? Starting with GenServers, you guys might have done this when you were learning how to use them. You can build a really simple one with a process, right? This is something that you can see happening. But GenServers out of the box come with the things that we would want it to do. It can start, stop, it can store state for us, it can help us run things concurrently, it can run both synchronous and asynchronous tasks, as we were hearing about earlier. When would we want to use something like this? So we can ask ourselves these questions. Are we going to need to store state? Do we need concurrency? Do we need to control for fault tolerance? And a bonus one, and this is, I think, where there is some stickiness around the should you use OTP, should you use GenServers. This is one of the ways I think you can tell is, are you going to be accessing that state a whole lot during the course of this process? Because remember that the GenServer is a process. So when we're thinking about that spy taking a message and performing a task, if we are sending a lot of requests to that GenServer and then we scale it, then that's going to cause a bottleneck for us. And thinking about these things ahead of time might draw you to use something like ETS instead, right? So if you're going to use a GenServer, you're probably going to want to supervise it because you're going to want to know if it fails. So generally with supervisors, what we do is we give it specific child processes to start at the beginning of the app. And we tell it how to restart these children if it fails. So what if we don't know at the beginning which children or how many children we're going to need it to start? What if we wanted instead to start those children in response to something rather than just at the beginning? So what they did is they made a whole module for that. It's called Dynamic Supervisors. And it's what we just said. It takes a child spec, start them up as needed. It can spin many of these up. If one of them dies, it can replace it with a new child. And what this really reminds me of, if we're talking about analogies, and don't worry, I'm not going to give you any spoilers, but I was watching Game of Thrones, and it kind of occurred to me that dynamic supervisors are like the Night King, right? Because he is somebody who has all these child processes, the zombies, and let's say that he knows when one of them dies. Then he can restart that zombie, right? That's like his whole power. And then he also can spin up as many other zombies as he needs because there's dead people all over the place. So he can just bring those to life when he needs them to. He can't make anything else. He can't make like cars or like tanks or anything, but he can make zombies. And so that's what a dynamic supervisor is. It's one type of child process available to spin up or restart as we need to. So this finally brings us to the app. We've gone through message passing, to the actor model, to early OO, into Erlang, and through the pieces of processes that build up into an abstraction of OTP. And we're finally at Course Deployer, the app that we were working on last year, where we used GenServers and dynamic supervisors, I think in a way that we can kind of learn from, or at least take some lessons to implement in our own apps if we're going to decide when to use OTP there. So this Course Deployer app, revisiting it, it's going to quickly try to clone a target GitHub repo, fork it for students, add some metadata to it, track the success or failure of each repo, and return the results to us so that if I deploy 10 lessons and 9 of them succeed, I don't need to redeploy 10 lessons. I just need to redeploy that one failed lesson. So that's the kind of information we want to surface at the end of this, right? So with everything we've talked about, we asked ourselves, should we use OTP in this? Well, are we going to need monitoring? Yeah, we need to know when a lesson succeeds or fails. Concurrency, yeah, we're deploying absolutely more than 100 lessons at a time. So we need this to happen at the same time. We need to hold on to state, because not only do we want to know if a lesson succeeds or fails, but we also want to know which step it succeeded or failed at. And we'll get to the steps a little later, but you can imagine there's a lot of API calls going on, and it's going to be helpful for us to know at which point they didn't succeed. Are we going to need fault tolerance? Yeah, we are, because we need to have the option of restarting something if we want to. We need to be able to control that on our end. And then this idea of limiting our access to state. So for this app, which we'll see, we're not going to be querying these GenServers a lot during their process. What we're going to be doing is asking them to return after they terminate, either they've succeeded or failed, the state. So we're not going to be doing this. It's not going to become a bottleneck for us in that way. And this checks all the boxes for us using it in our app. So let's take this sample course, Intro to Spying 101. we've got 4 lessons: disguises, accents, lying, and acrobatics. And we've got 4 promising students that we want to deploy these to. So we would have 16 repos at the end of this, right, for each of these students. This is the basic roadmap that we're going to take. We've got our course payload that we just saw on the previous slide. It's going to go into our course deployer app. That's going to put those repos on GitHub and return to us the success statistics of that last step. So to do this, we set up this type of supervision tree. We started with the course dynamic supervisor. This is going to have a couple different child processes. The first one is a GenServer to hold the course state. So throughout these 4 lessons being deployed, this GenServer is going to be the one where we dump the information about how they're doing during their deployment. Then it's going to spin up 4 separate GenServers for doing the work of deploying these lessons. You'll notice that we're separating this state and worker GenServers, even though GenServers, like we talked about, can store state, and we'll discuss that a little bit too. So this is a simplified version of what it would have looked like in our app. We've got this module course deployer, and when we call deploy course with those first course params that we saw, we're going to put that into the course supervisor's supervise state. So let's look at what that course supervisor module is. This is our course supervisor, and we're using dynamic supervisor, right? So when we're calling supervise state, then we're asking the dynamic supervisor to start the course state GenServer with the course params. So it knows what's happening there. Now, the next thing we're going to do is we want to deploy some lessons. So we go back to this course deployer module, and these are 2 more methods in here. Deploy lessons will take the grouping of lessons, it will iterate through them, and for each lesson, it will deploy it, which means asking our course supervisor to supervise worker. When we go back to our course supervisor, we can see that the supervise worker is going to also use dynamic supervisor to start a lesson worker, but because we've iterated through, we're getting 4 of those lesson workers. So the lesson worker, it's going to be doing all the API work. It's finding or creating an organization, creating webhooks, it's creating a team, setting permissions, repository, cloning the template. It's just got a lot of things it's doing, right? And at any point in this, you can imagine how one of these might go wrong. It's going to be really easy for it to fail. So what if something does go wrong? Well, throughout the course, we're going to be storing in that course GenServer, course state GenServer, the status of each of those pieces for each lesson. And like we said before, we've separated that state from the worker because these workers are doing so much work that can fail, and we want to protect the state that we have over here from one of these GenServers that might go down. So what might it look like at any point in time? We might have a state that looks like this, right? So we've got 4 lessons deploying for Jimmy 007. The first one, accents, seems to be about halfway through. Maybe it's created the organization or created the team. Acrobatics finished. That's great. Lying failed, and disguises is almost done. So what's a reason lying might have failed in this? That might have happened because of a race condition that it ran into, because we're using find or create organization. So maybe acrobatics and lying found it at the same time, but acrobatics was faster at creating it. So then when lying went to do that, the process died. That's okay. That's all right with us, because we can surface that to our user or we can restart it on our own. And we don't have to go through the guard clauses of figuring out what do I need to do to defend against this happening. We can easily just redo it. So then what we're surfacing by the end are 3 completed lessons, and then lying, which tells us exactly what it failed on, and then offers us a chance to retry it. So coming back to our initial question, how are we able to determine what the potential of processes can be in our application? I think there's a couple points that we can hit on. So the first thing is, I I really think that understanding the basic pieces of OTP behaviors is going to be super helpful for us in making that decision. Because once we kind of like go back through it, even if we're revisiting it and it's not the first time, and we remember that a GenServer is just a process and it can only do one thing at a time, then we're going to be less likely to reach for that GenServer to do some sort of like, guarding against or taking database requests or something like that, something that's going to be happening over and over again and more as we scale. So going through this exercise of remembering the pieces of OTP is the first thing that we can do to sort of prep ourselves for, should I use this here? I think that the second thing is really taking the time to understand our application's needs and asking those questions that we asked ourselves throughout this. Are we going to need to monitor things? Are we going to require fault tolerance? We're not always going to need those things. We're not always going to need concurrency in everything that we're doing. And we can rest assured that we're gaining a lot just by writing code in Elixir and running on processes. So if it does need those things, though, if it needs to run concurrently, if it needs to store state and monitor its processes, if we want fault tolerance out of all that, OTP can really give that to us. And I guess lastly, I want to really thank the panel earlier for having this discussion and acknowledging that like this is hard, right? This isn't something that we can read some documentation and be like, yes, my application fits these boxes and I know that OTP is going to work well for it. This is something that I think that as we learn and we build and we share our successes and our failures, we're all going to be able to figure out those boundary lines together. And it will help everybody the more that we actually try this kind of stuff out. I think there is some contention between whether you should be more careful about OTP or whether you should try it even if you're not sure. And I would probably lean towards the try it if you're not sure, because it's new for a lot of us and we need to play around with it before we figure out really what those lines are. So I think that this is going to, as we grow together and as we continue sharing these things, it's going to get us all closer to figuring out when we can determine like the proper potential for processes in our applications. And that's all I have, guys. Thank you so much. This has been great.